AP Chemistry molar conversions, gram to gram and molecular. These are typically 3-step or more conversions. Now I'll show you the traditional way of doing it, which I think is a little cumbersome. Be sure to check out the reaction table method. I think you'll find out it's quicker. But just for the sake of completeness, let's show it both ways. Here is the conventional way of solving these problems. Let's imagine we're burning some butane, and here is the molar ratios required. Convince yourself it's balanced. And here's a question we want to answer. We grab 100 grams of butane, which you can buy at most convenience stores, and we react it with oxygen. We overcome that activation energy by sparking it, and it should ignite, producing carbon dioxide and water. The question is, how much carbon dioxide will it make? Now, the conventional way to do this is to recognize that it's a 3-step gram-to-gram conversion. We can try to think it through. 100 grams is a little less than 2 moles, but every mole requires 6.5 times as much that weighs 32 grams. Those are the numbers that are going to be at play. Since it's 3 steps, it's hard to jumble that all in your head, so we'll start with what we're given. 100 grams of butane, recognize it's a 3-step conversion, and find our way to grams of carbon dioxide. Well, we have, as we said, a little less than 2 moles, since 58 grams is a mole, but every time we burn 2 moles of butane, see the numbers in front, it's going to produce 4 times as many moles of carbon dioxide. You certainly could convert this to 4 and 1. And that mole of carbon dioxide, notice top left to bottom right, units canceling, will have a mass of 44 grams, 12 plus 16 plus 16. Punch that into your TI-84 and you should see that after your units cancel nicely, it's enough to make 303 grams of carbon dioxide. Let's do another one. This time we're starting with 453 grams, that's a pound by the way, of butane, and we want to know how much water it will produce. So be careful to go where you need to go. Practice this one on your own if you like. Start with what you're given. Recognize it's a 3-step conversion. And in this case, work your way from grams of butane to moles of butane. Recognize that every 2 moles of butane will produce 5 times as many. The last question was 4 times as many, but it'll produce 5 times as many moles of water. And each mole has a mass of 18 grams. Notice we are going to H2O as instructed rather than the CO2, and you'll find that we have enough to make 703 grams of water. As I've said before, check out the reaction table method at some point. I think you'll find it's better, but it's nice to know both ways. Finally, we can even do molecular conversions. A microgram is barely visible. Imagine we have 1 microgram of butane. That's a millionth of a gram. We light it on fire, and this time I want to know not moles, but molecules of carbon dioxide that will be produced. Research has shown that the AP students have struggled with this one because although they can oftentimes do the standard conversions, they have trouble visualizing molecules. So let's check it out. Where do we start? With what we're given. So start with your microgram of butane and recognize that you need 1,000,000 micrograms to equal a gram. Now, if you were smart, you could have just said 10 to the minus 6 grams and skipped that step, but you get there either way. And how many? A gram of butane, well, you need 58 to equal a mole, so we have way less than a mole. And we want to know how many molecules of carbon dioxide will be produced. Well, as we saw from the previous problems, it's a 4-to-1 multiplier. Every 2 moles of butane will produce 4 times as many molecules, or 4 times as many moles of carbon dioxide. And what does it weigh? We don't need to go to where it weighs because we're going from moles to molecules directly. And that's a common error. See how I almost made it there? A mole is a number, 6 times 10 to the 23rd, and that'll give us directly, since everything cancels, now top left to bottom right is designed to cancel, and it should give us molecules of CO2. It's always a big number. And in this case, we'll get about 4 times 10 to the 16th grams of CO2. I do want to emphasize one more time that I no longer solve problems like this. I use the reaction table method, so be sure to have a look at it.